let's form a polynomial in standard form. So we're going to have to do some algebra here. What letter we're on here? H. Here is the polynomial. It has zeros at 1, -2, and 3 with degree 3. We'll start off with a pretty easy one here. Okay, so it tells us what the zeros are and says the degree of this thing is 3. So we want to write the polynomial in standard form that does that. So if they tell us the zeros of this polynomial, then that tells us what the factors are for that polynomial. What would be the factor that would get a 1 as the 0? Be x minus 1. Because if I said x minus 1 equal to 0, I'd solve it, I get 1, right? So it's the opposite sign. That's what happens here. When you get the zeros, change the sign. So that'd be x for the -2 would be x plus 2, and for the 3 it'd be x minus 3. Okay, so we can build the factors that way. That's what's called intercept form. We want to put it in standard form, which means multiply it out. Okay, so we got to do a little algebra here. I'm going to multiply these two together first and then distribute the x minus 1 because I think that'd be easier. So x times x, excuse me, x squared minus 3x plus 2x, last one's minus 6. I'm going to go ahead and simplify that before I do my distributing, just to make it a little easier. So I combine those like terms in the middle there, -3x and +2x, and got -1x. And then I'm going to distribute x minus 1 to all those. So I'm going to distribute x first. So x times x squared is x cubed minus x squared minus 6x. And then distribute -1. 1, 2, 3. So that'd be minus x squared plus, video does not seem to be wanting to work today, plus 1x plus 6. Good news is I've recorded this lesson several times, so I've got something I can share with you. Not a big deal. All right, and then I combine like terms, and I've got standard form. X cubed minus 2x squared minus 5x plus 6. There's my polynomial. Now, how can I be sure that that is the correct polynomial? What's a quick and easy way to check that? Where did I start with the thing? It told me what about the polynomial? That it had zeros at 1, -2, and 3. So what does that mean about that polynomial and its graph? Not turning points, but places that it crosses what? The x-axis. So if I were to just take my polynomial that I get at the end, if I graph it, if it doesn't cross at those same numbers, it's wrong. It has to cross at 1, -2, and 3 to be the right one. So if I type that in, x to the third minus 2x squared minus 5x plus 6, and I hit graph, I'm going to hit zoom 6 to get it back to the normal looking window. And here we see that thing crossing at -2, at +1, and at +3. That's the right places. Not very likely if you mismultiplied somewhere, you getting a polynomial that does the right things at the end. Okay, so and we can see with this one the degree was 3, so we knew it should have a maximum of 2 turning points. those turning points are these here, where at the top of that graph and the bottom of that part there. Those are the turning points that are happening there. But again, we're just kind of tying everything together that we've done. Okay. Let's do another one. Same section, same idea, same same stuff. And then we'll get into breaking down some polynomials. The zeros are -3, in parentheses, multiplicity of 2 and 5 with a degree of 3. All right. This one's a little tougher because they throw in that multiplicity idea, but they still say it's a degree of 3. Okay. So the first thing that I want to do is build the factors that go with the zeros or the x-intercepts or the roots or the solutions. Zeros is the more modern term out of that, but all those others mean the same thing. So if you were to Google help for this, if you find something that talks about roots, it's the same thing. Okay, nothing new. Okay, so what would be the factor for the -3? X plus 3 and then squared. Good job. Perfect. What would be the factor for the 5? X minus 5. Now, when I multiply all this together, it's going to end up being a polynomial of degree 3, because I know when I square x plus 3, I'm going to end up with something with an x squared on it. Man, this cable is about to fight. All right. Now, what does it mean to square x plus 3? Yeah. And my suggestion is go ahead and write that out. And there are shortcuts to squaring a binomial that you may or may not know, and may or may not be faster if you do know them. I don't think they're any faster, so I usually don't even talk about working on learning the shortcuts. So multiply. I'm gonna multiply the x plus 3 and the x plus 3 together first, and then multiply x minus 5 by that. So x times x, x squared. X times 3 is 3x. Then the same thing. 3 times x is 3x. 3 times 3 is 9. Okay, so I'm just multiplying out the x plus 3 times x plus 3. And then I'm simplifying that one to get x squared plus 6x plus 9 and x minus 5. Now all I got to do is do some distributive property. And it doesn't matter whether you distribute the x squared plus 6x plus 9 to the x minus 5 or do the x minus 5 to the trinomial. It doesn't matter. It's the same math. I'm just going to say, well, x squared times x is x cubed. 6x times, or x squared times -5 be -5x squared. Then 6x times x would be plus 6x squared. Excuse me. 6x times -5 is -30x. And then the 9 plus 9x minus 45. So I just distributed each term one at a time. And then I want to simplify that and get all the like terms together. And I'm done. So x cubed plus x squared minus 21x minus 45. If I look at the graph of that, x raised to the third plus x squared minus 21x minus 45. Hit graph. I see it. Excuse me, crossing the x-axis. 1, 2, 3, 4, 5. Positive 5. That's the right spot. And then what's it doing here at the -3? Is that doing the right thing? It's bouncing off of it because that has multiplicity of what? 2, which is an even number. So if the multiplicity is even, it's going to bounce off the x-axis. Okay? All right. Boom. Section 1 done. 2 more to go. All right. Let's get into actually taking polynomials and breaking them down into their factors and their pieces. So we got to do a little bit of fun math here. Me, I'm not getting along. How is that possible? I'm about to pull a cord out of somewhere else and use it. All right. Now, 5, 2. Real zeros of a polynomial. Real zeros of a polynomial. 5, 3 is going to get into complex zeros of the polynomial. So we're going to learn the basic skills in 5, 2 about breaking down a polynomial. One of those skills is long division. It's not something you're going to use a ton in this chapter or in this particular section, in these 2 sections, but the skill set that it takes to do long division with polynomials is similar to the skill set you need to do synthetic division. So I want to show you this because later on in chapter 5, you're going to have to do some long division too. So since we're doing division here anyway, let's go ahead and get the long division skill set out of the way. So what we're going to do is we're going to take 2 polynomials and divide them. So we're going to divide f of x equals x to the 3rd power minus 4x squared minus 5 by g of x, which is x minus 3. Okay. So old school, elementary style, long division of this problem. That's the problem we're doing, is that polynomial divided by that other polynomial. Okay. Now, you remember the long division symbol when you were a kid? Hadn't done that probably in a long time. We tend to do all of our division with our calculators now, and that's awesome. But polynomials we cannot do with the calculator. So we want to do this. So what you do is you put your divisor or what you're dividing by on the outside. And one of the things you've got to be sure of is you've got a representative from every power, starting with the biggest one in the divisor. So the biggest power in the divisor is x to the 1st power, and then there's an x to the 0 power of the 3. There's not an x, that's constant. So that one's okay. It doesn't need anything added to it. On the dividend, or what you're dividing into, this one has an x cubed, an x squared, and then it doesn't have the plain x. It's got the minus 5 in there. So we've got to put a plain x in there. So we got x cubed minus 4x squared, and then I'm going to put plus 0x minus 5. So if there's a missing piece, you got to put a representative in its place. That carries over when we start doing synthetic division next, which is much easier than long division, no doubt. You've got to have a representative for every power of x, okay? Starting with the largest one in each piece, okay? Now, long division is all about multiplication. When you did long division as a kid and you were just told to take 9 and divide it into a number like 107, something like that, what did you do? Well, you looked at the first number. Does 9 go into 1? No. Does 9 go into 10? Yes. How many times? 1 time. So 1 time. 1 times 9 is 9, and then you subtract it. I remember doing it like that, and you got a 1 left over, and then you drop the 7 down. And you said, what times 9 will get close to 17? Well, 2 will, but that's too much, right? 2 times 9 is 18. So it goes 1 time again, and I multiply and subtract. and my remainder is 8. And you had a remainder of 8. I remember doing it, that's been a long time ago. Okay? Now, with polynomials, it's all about the multiplication part. Okay? You look at the part in front. So the x here. What times this x will get me x cubed? The minus 3 does not matter. It's all about the part that's in front. X squared times x will give me x cubed. So I'm going to put an x squared up here. Just like in the long division with numbers, I took what I put up on top and I multiplied it to what was out in front. I'm going to do the same thing here. What's x squared times x? It's x cubed. What's x squared times negative 3? It's negative 3x squared. And then I'm going to subtract that whole thing. Okay? So I'm subtracting all of that from what's up top. So x cubed minus x cubed, those cancel each other out. That's what I wanted to happen. Yippee, they're gone. Negative 4x squared minus negative 3x squared. That's a double minus. So it's negative 4x squared plus 3x squared, which is negative 1x squared. And then I bring down the plus 0x. The next piece brings down. And then I go back to the front and I say, okay, what times this x would get me the negative 1x squared? Again, the minus 3 doesn't matter. All about the stuff in front. What times x gets me negative 1x squared? 1. And then another x, right? But I need a negative 1, right? So I'm going to do negative 1x. Yes, that's right. That's how we end up with the minus 1. So it's negative 4x squared minus a negative 3. So that became a plus 3. That's right. Okay? Now, I'm going to take this part. I'm going to multiply it to the stuff in front. So negative 1 times x would be negative 1x squared. Negative 1 times negative 3 would be positive 3x. I'm going to put that stuff in parentheses and subtract, because I'm subtracting that whole thing. The x squareds better cancel out. That's what I'm made happen. Okay. The next thing is 0x minus 3x. 0x minus 3x. That'd be negative 3x, right? 0 minus 3, negative 3. And then I'm going to bring down the minus 5. Then I go back to the beginning. What times this x here gets me negative 3x? What times x gets me negative 3x? Negative 3. So a minus 3 goes up top. Multiply it out. Negative 3x, positive 9, and I'm subtracting. Negative 3x minus negative 3x cancels each other out. Negative 5 minus positive 9 will be negative 14. And that's my remainder. Okay. This is my remainder. I know it's my remainder. I can't divide into it anymore because there's nothing times x that would give me something without an x, right? That's why I know I'm done doing the division part. Now, the way we write our remainder, since it's polynomials, is we put a plus sign, and then we put the remainder up top, and what we divided by on the bottom. And this stuff up here is our solution. That long division is not an easy thing, no doubt. But the synthetic division, you'll appreciate it more after you've seen long division for the problem. Okay. So remainder always going to be on top of the fraction. So it's kind of like writing a mixed number. For a long division problem like the one with the numbers, this would be the same thing as writing it as 11 plus 8 over 9. That's the same thing. In elementary school, we took the plus sign out of it and wrote it as a mixed number. You remember doing that? But there technically, mathematically, is a plus sign between those. They just never. The shorthand is you don't have to write the plus sign. That's what we're doing there. Okay. All right. Let's look at synthetic division, which is the tool you're going to use for this section and the next is synthetic division. So let's look at that tool. Okay. Synthetic division, much easier because you don't have to deal with the variables. Synthetic division for x cubed minus 4x squared minus 5 divided by x minus 3. We're going to do the same problem. So we better end up with the same answer, right? Show you synthetic division with this problem, okay? So synthetic division works similar to long division. Here's your setup. Make yourself a little bracket that looks like that. It's kind of laying down L. It's got a little shelf on the side here. Okay. On the inside, on the top row of that, chair won't roll. All right, there we go. On the inside, we're going to put the coefficients of the polynomial we're dividing into. So the coefficient of x cubed is 1. X squared is negative 4. What's the coefficient of x to the first power? Since it's not there, it's 0, just like it was in the long division. Got to have a representative. If the degree is 3, you got to have a cubed, squared, x to the first power, and then plain x. And then we have a minus 5 right there. Okay? So it takes all the letters out of the problem, which makes this a lot easier, it seems like. Okay? Then I'm going to take what I'm dividing by and set it equal to 0 and solve it. This is the number that goes on the shelf. When I set the divisor equal to 0, what I'm dividing by, set it equal to 0 and solve it, and that's what's going to go on the shelf. When I say, what's your shelf number? I'm talking about what number goes out there on the outside. Okay. Now, the next thing to do is do synthetic division. And the way synthetic division works, take this first number and drop it down, always. You don't do anything to get it down there. It just drops down automatically. And then you multiply. What's 1 times 3? 3. And that goes in that spot. And then you add. You don't subtract, you add. Synthetic division, addition, and multiplication are what you use, which kind of helps keep from having those double negatives and all that stuff. So it makes synthetic division much easier. So multiply and add. So add positive 3 and negative 4, we get negative 1. Then we multiply negative 1 times the 3. It's negative 3. Then we're going to add 0 plus negative 3 is negative 3. Then we're going to multiply. Negative 3 times 3 is negative 9. And then we're going to add. Negative 5 plus negative 9 is negative 14. This number that's in that spot, that last spot, that's our remainder. What was the remainder when we did this with long division? Negative 14 is the same number, right? So synthetic division, long division, both get the same answer. but that was a lot easier work, wasn't it? One in front of the x cubed there. Negative 4 is in front of x squared is there. There's not a plain x, but I need a representative for it, so I put a 0 in its place. And then the -5 is the constant. So it's always just going to be the numbers that are in the front. If there's a missing piece, put a 0 in its place. Always. And then what you're dividing by, set it equals 0. It always changes the sign. But if it were like a fraction, you could end up with a fraction. Get that. And then here, this becomes our quotient and remainder. So when you do synthetic division, it always takes the degree down 1. So we started with x cubed. So the answer starts with x squared. So this becomes x squared minus x minus 3 plus negative 14 over x minus 3. That's the same answer that we got up on example A, right? We take the degree, synthetic division takes the degree down 1, always, 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 okay? We can only use synthetic division if our divisor is linear. If the divisor is something quadratic, then we can't do it that way. But for what we're doing with polynomials, it's going to be linear that we're dividing by anyway, okay? Now, we're going to practice some synthetic division as we go along, and we're going to use this thing called the factor and remainder theorem. My cousin went to graduate school at LSU, and he's a computer science guy. So, but he had to take some math classes in his graduate work to get his master's, and he said, I learned 2 things about graduate level math courses. Number 1, if on the first day everything they said is prove this, prove that, change your schedule. And he said the other thing was never take anything with theory in the name. and theorems are what we were having to prove, and they're based on theories. So the factor and remainder theorem, I'm not asking you to prove it. We're going to use it. What it tells us is that x minus some number, we're going to call it c, x minus c is a factor of a polynomial if and only if, that's a pretty strong statement there, f of c equals 0. What this says is if you do division by x minus c, gets a remainder of 0. Okay. Then x minus c is a factor. That's what that says. Okay. So we're going to do division by a something to decide if it's a factor or not. Okay. So let's take an example of that. Example C is x minus 1 a factor of, here's our polynomial, f of x equals 2x to the third minus x squared plus 2x minus 3. Okay. We're wanting to decide, is x minus 1 a factor of that? So the deciding if something is a factor, the way to determine that is to do division by that factor or possible factor. Okay. And we could do long division if we wanted to, but long division, well, it stinks. it takes forever to do. It's a lot of writing. It's a lot of negative signs that we don't need, right? So because x minus 1 is a linear piece, it doesn't have x squared in it, I can do synthetic division with that much easier. So that's how I'm going to do my division with this. I'm going to break that polynomial down by using synthetic division. So I'm going to set up my synthetic division, and then what are the numbers that go on the top line on the inside? So the numbers that go in here. What's the second one? -1, 2, and -3. Okay, so this is the coefficients. We didn't have to put a 0 in on this one because it was everything was there. We had x cubed, we had x squared, we had plain x, and then a regular number. Okay, so we didn't have to put any zeros in the place. What goes on the shelf? +1 or -1? +1, because it changes the sign. If I were to set x minus 1 equal to 0 and solve it, I get +1. So +1 is up on the shelf. Okay. Now we're going to run synthetic division through this polynomial. I'm going to drop the 2 down, and then what do I do with that 2 and the 1 that's on the shelf? Multiply. So that gets me 2. What do I do with the -1 and this red 2 that's underneath it? It's not red on your screen, but it's red on my screen. You add. So that's +1. Multiply. Add. Multiply. Add. That number on the end there is the remainder. If that remainder is 0, the factor and remainder theorem tells us that, hey, that is a factor of the polynomial. Okay, so x minus 1 is a factor of the polynomial. And here's where this is leading us, okay, is that we can break a polynomial down into smaller factors, and then once we get it into smaller factors, it becomes an easy problem like we did here. When we got all the zeros of it, we just set the factors equal to 0, right? So if we can get it factored, getting the zeros is an easy thing. So where we're headed is we're going to say, oh, well, if x minus 1 is a factor of that, then f of x must be x minus 1 as a factor. And then we'd have a quadratic left. 2x squared plus x plus 3 is the other part. This and this, that's where those are coming from. Okay? And then that's a quadratic. And because that's a quadratic, I've got a lot of tools for solving quadratics. I've got quadratic formula. I've got solving by square roots. I've got factoring that I could do for quadratics. So the idea is that we're going to take larger polynomials and break them down using synthetic division until we get a quadratic, and then we can use quadratic tools to work up the quadratic tools. And so it's going to take some synthetic division to get to the end of the result. Okay, so now when we're checking to see if something is a factor, the remainder has to be 0. So we've got to have that rule established. So this establishes that rule that if we do division and the remainder is 0, then it is a factor, and that allows us to break the polynomial down a little further, like this stuff here. Okay? So what we're going to do now is we're going to take a polynomial from scratch, and we're going to try to find our own factor out of that. Okay, so find all the possible rational zeros. And this is where the graphing calculator is going to help us some. And factor the polynomial and here's our polynomial. F of x is equal to 2x cubed plus 11x squared minus 7x minus 6. That's our polynomial. Okay. what we're going to do is we're going to list all the possible rational zeros. So this is what's called the rational zeros theorem. You don't necessarily have to know the name of the theorem or anything, but it's the rational zeros theorem. What it tells us is that we do P over Q, and P are the factors of P over the factors of Q. And in our problem, P is always the constant on the end, and Q is always the leading coefficient, the coefficient in front of the highest power of X. So factors of 6 over factors of 2. Okay. What does it mean to be a factor of 6? Not that you can divide it by 6, but you could divide it into 6. So like 1 is a factor of 6 because 1 goes into 6. 2 is a factor of 6 because 2 goes into 6 an even number of times. Okay. So the factors of 6 are 1, 2, 3, and 6. Technically, plus or minus in front of all of those. I'm doing a little curly brace things again. Technically, there's a plus or minus in front of all of those. What are the factors of Q? For us, Q is the number 2. What are the factors of 2? 1 and 2. That's it. Nothing else goes into 2 but those numbers. Okay? Now, the way you get your actual list is you take the numerators and divide them by each one of the denominators individually. So I take 1 divided by 1. That's 1. 2 divided by 1. That's 2. 3 divided by 1. That's 3. 6 divided by 1. That's 6. Okay? Then I divide them all by 2. 1 divided by 2. That's a half. 2 divided by 2. That's 1. I've already wrote that down, so I don't have to write it again. 3 divided by 2. That doesn't go evenly, so I'm going to write 3 over 2. And then 6 divided by 2 is 3, and I've already got that written, so I don't have to write it again. Technically, there's a plus and minus in front of all of those. Okay? So our P over Q list, our possible rational zeros, we've narrowed down for this polynomial from every number in the world to a list of 1, 2, 3, 4, 5, 6, technically 12 numbers, because you got positive and negative on each one of those numbers. So we've narrowed it down from every number in the world to these 12 that could be the zeros. Now, when I was in school, we had to guess and check. And if it didn't work, you guess another one and go from there. You guys have a graphing calculator, so it's going to shorten this up quite a bit. Okay. So what we want to do, what this means, the possible rational zeros means if it's a rational zero, then it's got to be one of these numbers. Okay. So that narrows down which ones it can be. What we want to know is where does this polynomial cross the x-axis? It should be, if it's a rational one, it will be on one of these 12 numbers. So we're going to graph the polynomial and see where it crosses, and that's going to help us use one. Okay, so I'm going to the graphing calculator. I'm hitting y equals, and I'm typing in that polynomial, 2x to the third plus 11x squared minus 7x, then minus 6. And I'm hitting graph. All right. Now, we can see it crossing the x-axis in 3 places. Okay? We just need to pick one to start with. My suggestion is don't pick a fraction if you can help it, because that makes it hard to do the synthetic with, right? Anytime you got to work with fractions, it's tougher. So pick one of the nice ones. It looks like it's crossing at positive 1 right there. So that's the one I would pick to start with. I can verify that it's crossing at positive 1 by hitting the trace button on my calculator, which is right beside the graph button, and then typing in positive 1 and enter. And notice how it gives me that ordered pair down at the bottom, 1, 0. That 0 on the Y tells me, hey, that's the one you want to use. Okay. If I got any other number there besides 0, that means it didn't work. Okay. So I know it's crossing the x-axis at 1, so I can use that in my synthetic division to start breaking this polynomial down. So that's what I want to do. So I'm going to set up my synthetic division, make my little laying down L, shelf. My number I'm going to put on the shelf, I already know it. It's +1. That's one I found on my graph. Okay. I'm going to put the numbers 2, 11, -7, -6. Those are the numbers from my polynomial. And I'm going to use synthetic division to break that down. Drop the 2, multiply and add. I get a 0 in the remainder. That should not surprise me. That means I did it right, because I already knew that it crossed the x-axis there. All right? So that's good. What that does is it takes our polynomial from that cubic polynomial down to this polynomial. Okay. Now, how did I know it was x -1 as the factor? Exactly right. It's a +1 on the shelf. It always changes the sign in the factor. Okay. Now, the next thing I want to do, since it said it wants me to factor this polynomial, is I want to factor that quadratic. So remember factoring quadratics? That was the X method thing I showed you last week. 2 times 6 is 12. That's how I got that number. And then 13 goes on the bottom. So I need numbers that multiply to be 12 and add to be 13. So that'd be 12 and 1. 2x squared plus 12x plus 1x plus 6. And then I'm grouping. So it'd be 2x, x plus 6. The second group only has a 1 in common, so I'm going to pull a 1 out. X plus 6. And then my factors will then be x plus 6, 2x plus 1, and then x minus 1. There is the factored form of that. What are my other zeros? So this will be example E. Same problem, we're just going to extend it. What are the zeros to f of x equals 2x cubed plus 11x squared minus 7x minus 6? That's the same polynomial we just did for example D. Okay, we did the factored form there. What do I do with each factor to find the zeros or the x-intercepts or the roots or the solutions? Equal them to 0. So if I take this whole problem, set it equal to 0, that allows me to do that. So I got x minus 1 equals 0. I know that one already. X plus 6 equals 0. And 2x plus 1 equals 0. Solve them. X equals 1. X equals -6. And then this would be x equals -1/2. When I look at the graph of this polynomial, where's it crossing the x-axis at? At all those numbers. Okay? So the graph, if it crosses in 3 places and the degree is 3, then they're going to be the answers are going to be those. It doesn't always do that, though. It doesn't always cross the same number of times as the degree is. We'll see how to deal with that in just a minute. But the idea here is your graph and your factored form and your zeros all line up. It's not a coincidence that they're all the same. They should be. If they're not, something is really wrong. Okay? So they're all should line up there. Okay? So we found the zero by taking the factored form and solving those, set them an equal to 0 and getting the answers for that. So that's how you're finding the zeros of a polynomial is we're going to factor it completely and then set because once you get it factored, that's the easy part. The factoring is the hard part. Okay, so let's do a tougher one for the factoring. Let's do another one here. So here's our function, f of x. Let's do a fifth degree problem. X to the fifth minus x to the fourth minus 4x to the third plus 8x squared minus 32x plus 48. Now, first thing that I want to do is do my P over Q list. So that helps me know what to even try. Okay. On the quiz, on the test, on the final exam, there will be questions that ask just for this list. You don't even have to do anything with it, just make the list. Every time I've ever taught Math 140, that's been on the final, at least one question, if not two. Okay, so make sure you can make this list. It's too easy not to do. All right, so what's P in our problem for this particular polynomial? 48. P is always the constant on the end. Q is always in front of the highest degree. So Q for us on this one is 1. So we need the factors of 48. Now this is where it gets tough because you got a lot of factors in the 48, right? So I like to think about it in pairs because the factors of 1 is the easiest. 1. Nothing to that. But the factors of 48, you got 1 times 48 is 48. 2 times what? 24. How many times 3 go into 48? 16. 4 goes into 48 12 times. 8 goes into 48 6 times. I can give myself enough room. I'll write the 6 over here. It doesn't matter. Okay. 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48. Those are the factors of 48. The bigger the number is, the more you got to check, right? So the more you familiar you are with your multiplication tables, the better. Now, our P over Q list is going to be plus or minus just the numerator there because you divide them all by 1, right? So plus or minus 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48. So we've narrowed it down for this big polynomial from every number in the world into 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 numbers. Just still a lot of numbers, but we're going to narrow it down more by looking at what part of this polynomial. What do we look at next? After we get our P over Q list, we got to have something to put on the shelf. How do I get a number to put on the shelf? How did I do that on the previous problem? See where it crosses the x-axis. Get an idea from that graph. Instead of guessing at it and just randomly picking a number, we're going to get a graph and look at that and see where it's crossing. We're going to try to find a good number, okay? So I'm just going to go to my y equals menu on my graphing calculator. I'm going to type in x raised to the fifth minus x raised to the fourth minus 4x raised to the third plus 8x squared minus 32x and then plus 48. Get graph. Now, here's what I've got to notice. What's going on at positive 2? It's bouncing off. So what's that tell us about positive 2? It's got a multiplicity that's even. That's exactly right. It's either 2 or 4 times, right? Okay, so what that means when it comes to synthetic division is that I can use 2 multiple times, twice, maybe even 4 times. Okay, don't know that yet until we get into it. All right, so that means I can use the 2 more than one time. I could also use -3. I see it crossing at -3 there. So both of those numbers can work here. So what I'm going to do is I'm going to start with the 2, and I'm going to run it through there the first time. And use synthetic division. 1, multiply and add. Multiply and add. Multiply and add. And if I don't get a 0 in the remainder spot, I know I miscalculated somewhere. Okay? Got to get a 0 in the remainder spot. All right. Now, because I know 2 has a multiplicity that's even, I know I can use it at least one more time. So I'm going to break that down one more time. I'm just going to do a synthetic division again on those coefficients, and I'm going to put 2 on the shelf again. All right. Now, run exactly the same way, just using these numbers. So 1, 2, add up, multiply. And there's that 0 on the remainder on that one. Okay. So here's what's happened. So far, I've done 2 synthetic divisions. Every time I do a synthetic division, I started with an x to the 5th power. That's what this one was, right? When I did a synthetic division one time, it took this down to x to the what power? 1 below. Took me down to x to the 4th. So when I did this synthetic division, this is now x to the what? X to the 3rd. Okay? I want to get it down to x to the 2nd power because I get a quadratic, and that opens up quadratic formula and all of the things that I know about quadratics that we did in chapter 4. Okay, so what number could I put on the shelf and do this to get it down to a quadratic? What was the other place that crossed the x-axis on my graph? -3. So that's what I'm going to use on the shelf here. It's possible that 2 works again, but be honest, 2 times is a pretty good fit for it to work. It's not likely that you're going to get a 0 that works 4 times or 5 times or, a whole lot of times. Okay. If it's an odd multiplicity, then it working, 3 times is a lot, actually. Okay. So twice is about the most you're going to see. Now, we're going to run synthetic division with a -3. So I'm going to drop the 1, multiply. Add. Hey, there's a 0 right there. That's easy multiplication. Makes for easy addition. And there's the -12. And there's the 0 in the remainder. What this has done is taken this polynomial and got me factors x minus 2, x minus 2, x plus 3. And then what's this, that little jewel right there? What's the factor that it has? Because remember, I started with the 5th power. This one was a 4th power. That's a 3rd power. So this has to be a squared. So that's going to be 1x squared plus 0x plus 4. I have taken this polynomial and factored it using synthetic division and the graph to help me out. Okay? Now, all I've got to do to find all the zeros of that polynomial, or all the roots, or all the solutions, or all the x-intercepts for that, is set each factor equal to 0. I already know the answers to these three, right? I know that x equals 2 with a multiplicity of 2, so x equals 2, and we'll abbreviate multiplicity of 2 like that. So there's one of our answers. We know x equals negative 3. All I got to do is solve this one. X squared plus 4 equals 0. That's the one I don't know yet. Or the two I don't know yet, actually. How can I solve that? What are my methods? Okay, so before I can take the square root, what do I have to get by itself? Yeah, so I'm going to move the 4 by subtraction. That's right. That's the way I would have done this one. And then she said I could take the square root. So if I take the square root, remember I got to put a plus or minus in front of it. What's the square root of negative 4? Remember when they take a square root of a negative, it's an I. What's the square root of 4? It's 2. And it's got the I on it. How many answers should I have? Since the degree of the original polynomial was 5th degree, how many zeros should I have? 5 of them, right? So I've got 1. This one counts twice, so that's 2, 3. And then a positive 2i is 4. The negative 2i is the 5th one. We found all 5 zeros of the polynomial. Now, here's the kicker. When you look at the graph, how many times did it touch the x-axis? Technically 3, but it really only touched it twice. It crossed it at the negative 3 and bounced off at the 2, right? So we didn't see these on the x-axis. You won't see complex solutions ever in the graph. They won't cross the x-axis. Only the real ones cross the x-axis or touch the x-axis. Complex ones don't touch, okay? Now, the beautiful thing is that the next section is completely the same thing. It is no different. Why they didn't put them in one section? You got me. I don't know. I never understood that. Every college algebra book I've ever taught out of does the same thing. Let's take another polynomial. I'm not changing notes. I'm just going to the next example letter is G, and we're going to take f of x is equal to 3x to the 4th plus 5x cubed. We're doing this last one, guys. I promise. I know you got to get out of here. All right. Technically, you would need to make the P over Q list. You need the factors of 18 over the factors of 3. So 1, 2, 3, 6, 9, 18, 1, 3. You guys can do that part. We're going to take the shortcut here and go straight to the synthetic. Because how are we going to get a number to start with anyway? We're going to look at the graph, right? So be able to make the P over Q list, because you know there's going to be quiz question, test question, final exam questions about the P over Q. But we know to get started, we're going to get the graph and go there, okay? So that's our shortcut, okay? So I'm going to the graph, typing in 3x to the 4th, 3x raised to the 4th, plus 5x raised to the 3rd, plus 25x squared, plus 45x minus 18. Hitting graph. All right, I see some places it's crossing the x-axis. I see a -2 right there. And then That one's a little weird. It's close to 0, but it's between 0 and 1. If I think about my P over Q list, I'm pretty sure 1/3 will be in there, and that looks like about what it is. So I'm gonna use the -2 first for my shelf number, because I know it crosses there, and then we'll go from there. All right, so I'm gonna drop the 3 down, multiply, add, multiply, add, multiply, -54, be -9, and 18. There's my 0. Wonderful news. So that means -2 is a 0. This polynomial, x plus 2 is a factor of it. Now I'm going to go on my shelf. I want to verify that 1/3 is what that number is. So I'm going to go back to my graph, and I'm going to hit trace 1 divided by 3 and hit enter. And it got me the 0 on the y, so I know that that's the right number. Okay, again, I got that from my P over Q list, so that's where that comes from. Okay, now I'm going to put a 1/3 on the shelf. So we got a fraction to deal with. Don't have a choice. That's the only other number that crossed, right? So I've got to use that. So I'm going to drop the 3 and multiply. Well, that's easy math. That's a 1. And that's a 0. 0 times 1/3. I can do that too. That's 27 plus 0 is easy. 1/3 of 27. +9. And there's my 0 again. Here's what I'm left with. A quadratic to solve. If I solve this in the same way as I did the last one, take the square root. So I get zeros of -2, 1/3, and plus or minus 3i. Those are the zeros of my polynomial. When you break, here's what you need to know for sure. Degree minus 2 equals number of times you need to do synthetic division. Whatever the degree of the polynomial is, subtract 2 from it. That'll tell me how many times I need to do synthetic division. That's what, if you'll follow that rule, then it'll work out. Once you get it to a quadratic, either solve it by factoring, like this with square roots, or quadratic formula. Any of those ways, same ways that we used in chapter 4 to solve quadratics. Okay, that's the way that you want to solve these equations in these sections. Okay,